Okay, so good morning everyone. Welcome to this eighth lecture of Memory Design and Test course. So before we start, let's do a quick review of what we did in the last lecture. So what were we doing in the last class?
Sir, we were doing bump estimation, sir. We have derived the equation for the bump estimation. And
So what is this bump? Why does it appear?
sir, it
So I
appears.
want as many of you to participate, please. I do not want just two or three. Two or three are participating, it's good, but I want as many of you to speak up, please. Yeah. So Vaishnav, you're saying.
So bump appears when during the read cycle, sir. So while read cycle, so as we as the current flows into the circuit, so there appears a bump which might affect our stability during the write cycle. This bump might appear on the other part of the NMOS and it might turn it on. So yeah, we were seeing all the effects that were.
Yeah. So I know that you understand, but I don't think other people would have understood what you said. So someone else also, can you repeat?
So, for example, when we are reading, there is a cell current that flows into the our bit cell. That bit cell can lead to a slightly voltage appearing on the node that is storing a zero. And if we want to ensure that the voltage increase is not such that it flips the other inverter. So we want that it is below the VT of the NMOS, or we can think in terms of the trip point of the other inverter too. So we want to limit that increase.
Yeah, we want to limit that increase, and whatever margin we have between this bump value and the trip point of the other inverter, that is called as
Static noise margin, sir.
noise margin. Great. So that is where we wanted to estimate the equation as to how is this bump dependent on what all variables are we looking at?
Cell ratio, mismatch,
Cell ratio, mismatch.
BSS, high voltage.
Very good. Array voltage.
Yes, sir.
Yes, sir. Word line and bit line voltage.
Word line, bit line voltages. Very nice. And we saw that by just analyzing these equations, we can arrive at, or we can understand what is a write assist scheme, what is a read assist scheme. So why are these called as write or read assist schemes?
So
Because
like
they
as I
help-
okay.
So because they
Sachi.
help in improving the power consumptions and they help in improving the stability and all. So area is also one factor. So that's why we call them as assist schemes.
Okay. So see, when you will do the bit cell analysis and you will do bit cell designing yourself, you will see that if you really want something to operate at a low voltage, in the presence of mismatch, then you will need to increase the size of devices as you go to lower voltage of operation. As you increase the size of devices, what happens? Area increases. Area, we all agreed and understood, is the most important figure of merit of a memory cell. So we don't want area to increase. So what is the alternative? See, we had increased the sizes of devices so that they could now sink more current. They could become better, when they are turned on, they have more current flowing through them. So is size increase the only way to increase flow of current from a device? No. We know that whether it is subthreshold current or saturation current or linear current, W by L is just one of the component of that equation. There is VDS, VGS, so many other things which would define how much current would flow through a device. So when we improve the current through a device, and therefore circuit performance through a device, without changing the size, without increasing the size, but by changing the voltages, that is called as assist scheme. Assist because they are assisting a dense cell to operate at a voltage where it would have otherwise failed. Is this clear? Why are assist schemes called assist schemes? Any questions?
So I have one question from last class. So when we were talking about write assist schemes, we were changing the supply voltage. So by we have we have taken the example of VRA, VWL, VBL equal to 1 volt. And if we reduce it to 0.7, then our pass gate will become weak and V int will increase. So, and after increasing the supply, like you've taken 1.1, so the V int was increasing at that point also. So what was the reason? I am not able to get that.
So do you realize that over there also there is a kind of a voltage stack that is coming into picture from the VDD at the PMOS source?
Yes, sir.
To the PMOS resistance, on resistance, then resistance of the pass gate, and then the resistance of the right driver.
Yes, sir.
So it's also a potential divider.
Yes, sir. Yes, sir.
You change the voltage on the top, the source of the PMOS.
Yes, sir. Okay.
If nothing else changes, if all the other resistances also remain constant, even then, just because that voltage has increased, your V int would increase.
Achha, okay, okay. Yes, sir.
But I would say that is not the only reason. The reality is that the PMOS is in saturation region.
Okay.
When you raise the VDD, the current, the change of current in the saturation region is in one way.
Yeah.
Whereas the pass gate is in the linear region.
Yes, sir.
It will only change linearly as the voltage increases. The current through the pass gate would change only linearly.
So it is not, yeah. So it is not able to sync that much. That is
Yes.
okay.
Okay, so you can look at it in multiple ways, and all these things come in together.
Okay. Okay, sir.
Yeah.
Okay, sir.
So what was it that we did after this?
Right estimation.
Right estimation. Okay. So what are the right assess schemes that we talked about?
So word line overdrive.
Word line overdrive.
So bitline under bitline and bitline under bitline undershoot or negative bitline.
Negative bitline.
Negative bitline.
So V array lowering.
V array lowering.
Sir, VDD split.
VDD split. हमने क्लास में बात नहीं करी थी.
So this is not. So I don't know about this.
You must have read the paper there.
Yes, sir.
So yes, what we did was that is a patented solution where we say that depending on what we are writing on which side, we would split the array supply of the two PMOSs. We will not connect them for the same metal rail. We'll have two independent metal rails running for one PMOS and the other PMOS. And then the side which we are storing, where we want to store a 0, that particular PMOS will lower the VDD only for that. And the other PMOS will not lower the VDD. So we had applied TRIZ to arrive at this solution, and it was patented and everything. But yes, splitting. So if you want to know more about this, we did not discuss it in the class. You can read the paper on my Google Scholar page. Okay. What other right assess schemes could be there? What else could you change? You said you would change the supply voltage. What else?
VSS increment.
Yeah, we could raise the VSS. So when you raise the VSS, what happens?
So the V bump, the VX increases. So
it's almost like VDD lowering, as we discussed. VSS raising is almost like VDD lowering because the rail-to-rail voltage across the memory cell has reduced. So that can also act as a right assess scheme. Great. So after that, what did we do?
ROM cells.
ROM functionality. So we looked at the ROM cell and we saw how the programmation is done. We looked at two kinds of ROM cells, NOR cell and NAND cell. And we also saw that programmation as to, as a designer, you have to make choices of where to do the programmation. We saw in the NOR cell that when you program on the drain side, that is on the bit line side, you add a lot of uncertainty on the bit lines. Some bit lines will have large capacitance, others will have small capacitance. There will be some kind of power consumption from one bit line, another kind of power consumption on the other, and so on. Whereas if we were to program on the source side, we also remember that the bit line capacitance became constant. You remember this?
Yes, sir.
Okay. And then we looked at the NAND cell, And we said that NAND cell is denser than the NOR cell because the total number of contacts that you need to build is lesser. There is more active and OD region sharing. Therefore, NAND cell is denser than the NOR cell. So,
Sir,
yes.
Sir, I had a little doubt about the writing operation, but it has a fundamental. For example, sir, when we are writing, we are mostly looking at the writability part, which is we are focusing on the 0. So, sir, the other bit line, which is pre-charge to VDD, we essentially are basically not looking at that. For example, we are not saying, so can and also during the read operation, because in the early office hour, we were in the equation, we were modeling the VDS as VD Saturn. And when we go to the saturation, then the VDS doesn't come because ultimately it's saturated. So can I think of a kind of a situation in which the bit line, the VDD of the bit line, I can set it as a lower value than the other VDD kind of, because that would ultimately help with stability.
Yeah, bitline lowering is a read assist scheme. It is
No, sir, sir, it is, I'm talking in terms of read assist scheme, but like for example, sir, when I am designing the bit cell only, the memory, I am not, I doesn't take it as a separate assist scheme, but like a design is such that the bit line, I
So
don't
this,
charge the VDD only.
So this is called as co-design, Raghav. This is called as co-design of the technology, which is the bit cell. Bit cell comes as a part of technology offering. Okay, so this is called as co-design, where the design team will say that, okay, this thing I will always boost. For example, you may say word line I will always boost.
Okay.
Or bit line I will always precharge only to this level.
Okay.
Or when I want to go to low voltage, I will precharge the bit line to a lower level only. Don't worry about it. So then the technology team would say, okay, if that is the case, then we'll be able to make the cell still denser.
Okay.
Yeah.
So
it's
like it is
called
valid.
co-design.
Okay.
Yeah. It's called co-design.
Okay.
Okay.
And so I also had a doubt in the DROM cell. So actually, when we change to the VSS, the ground, we said that will put the contacts at VSS. So sir, there was in the slide was mentioned that some new figure of merits, but like I was not able to come to that.
Yeah.
What exactly could be?
Yeah. What could be the figure of merit? You tell me.
So I mean, earlier we resolved that problem that bit line now is uniform. The load is uniform across all bit lines.
But now all the cells are there which are connected. So the leakage comes into picture. In the earlier case, bit lines, the load was the figure of merit. What is the load? Every bit line would have a different load. Now every bit line has a different leakage.
Right. Yes, sir.
Okay. So you just need to see where is the design complexity that gets added. And that is where you define the figure of merit there. Okay, so that you can benchmark two solutions on the most critical aspect. Okay, so with the last class, friends, what has happened is we have kind of closed our discussions on memory cells. Okay, and now from today onwards, we are going into periphery design. So that is good news because now we are closer to the project definitions for all of you. So the TAs will now within I think a week announce some project titles so that you guys can enroll and choose which projects you form teams and enroll into projects. Okay, so that will happen anytime now. Okay, so I also want to give you another good news. See, till now we had Gagandeep and Bilal as the TAs of this course, but Amir has also volunteered to be a TA of the course, and he will be available on Thursdays from 4 to 5 p.m. His office hours will be on Thursdays from 4 to 5 p.m. So you can also take help from Amir if you have some additional queries or something like that. Okay. So he's not being he will not get any credit in terms of coursework or edit or neither in terms of money. He's already TAing for another course, but he said he would want to volunteer. So I think we should clap for him that he volunteers, and all of you stand to benefit there. So thank you, Amir. Okay. And then I would want to, okay. So now today we will start to look at circuits in the IO. So what are the circuits in the IO region that you know of? What does the IO region contain?
Sense amplifier.
Sense
Right
amplifier.
driver,
Sense amplifier, right driver.
Sense amplifier, right driver, okay.
Marks.
Multiplexers, okay. And
buffer,
The row decoder, the precharge circuit.
the
I-
latches for
Same buffers.
latches. I'm sorry?
Output buffer.
Input output buffer.
Input buffers, output buffers, very good. And socho.
Sir, lots of wiring, sir.
Lots of wires. Okay, good. And
Sir, charging and discharging of bit lines.
charging and discharging of bit line. Pre-charge circuits. So now, so that kind of rounds it up. We have when we talk of a memory IO, we have a wide range of circuits there. And those circuits essentially involve, how do we put it? Sense amplifiers, latches at the outputs of the sense amplifiers, input buffers for the right driver itself. Then we also have mux, which would connect the relevant bit line to either the sense amplifier or the right driver or both of them. And then we also have the pre-charge circuits. So let us have a quick look at. Yes.
Screen is not visible.
Oh, my screen is on. Just a minute. Is it visible now?
Yes, sir. Yes, sir.
Okay. So an IO would typically have this range of circuits in it. And as a designer, even when you are placing these circuits into your memory, you have a choice. You have a decision to make. For example, where would you want to place the mux? Would you want to place the mux above the right driver or below the right driver? So what is the difference? What happens differently when you place the mux above the right driver or below the right driver? Or when you place a sense amplifier above the multiplexer or below the multiplexer? What happens? What difference does it bring according to you?
So I think the loads will be different. Load seen.
Loads will be different. For what? What will see different loads?
If we are seeing on with the perspective of right driver, if it is placed like between the sense amplifier and mux, then it will see sense amplifier as the load. Now, but if right driver is placed like this right now, it will see mux as the load. So
for the right driver, where is the data coming from?
The mux.
Sir, external input.
Externally, we are providing.
It is coming from the input buffer, na? So the data is going up. For the right driver, the data is coming from the bottom, from the input buffer. And the path is like this, going up.
Yes.
So where would the load of a right driver be? Would it be down there or up there?
Okay, up there.
So what is the load of the right driver then?
Okay, so it is fixed. It is pre-charging.
Is it fixed?
It will see, yeah, pre-charge as the load now.
Let's just pre-charge the load. What happens to the bit line? There are bit lines running here.
Yeah, like, okay, now, okay, sir.
This IO is placed below the array, na?
Yes, sir.
So the array is always the load. So what else changes? Ranjit.
Sir, if the sense amplifier is placed after the multiplexer, then it can be a case where the performance can be hit, because and if the sense amplifier is placed before the multiplexer, the performance improves, but we'll have lot number of sense amplifiers for each bit line.
Wow, very good. So what Ranjit is saying is that if you would place the sense amplifier or the right driver below the multiplexer, you have only one right driver and one sense amplifier for all the bit lines that are coming onto that mux. So if it is mux 4, then you have one sense amplifier for 4 pairs of bit lines connected to 4 bit cells. However, if you would place the sense amplifier or the right driver above the multiplexer, then since multiplexing has not happened yet, each bit line will be connected to a sense amplifier. Each bit line will be connected to a right driver. So the area, so instead of one sense amplifier or one right driver, you will have 4 sense amplifiers or 4 right drivers in mux 4. So the area goes for a toss. We may improve performance a bit, but area definitely goes for a toss. So this, how and where you place your circuits in a IO, has a very strong bearing on area and performance trade-off. Are you able to see this? Any questions?
Sir, in the sense amplifier, we are basically sensing the differential voltage that is appearing. So how my performance will increase? Because I can set the differential to even after the mux, I can sense a differential with that. I mean,
yeah, but a multiplexer means additional resistance coming into picture. So additional RC delays will come into picture. है ना?
okay, yeah.
Bit line is a small swing signal. Bit line is a small swing signal. So the multiplexer that you will need to make cannot be a digital multiplexer per se.
Yes, sir.
So that is why it can. So because it's a non-digital multiplexer, and when you place the sense amplifier or right driver below the multiplexer, resistance comes into picture, and that is what we're talking about. Okay. So anything else? Any other questions?
Sir, the right driver should be below multiplexer, right? In this image.
No. Did I say that? No, I did not say that. I simply said you can put the right driver above the multiplexer, but then you will have to put 4 right drivers instead of 1 when it is mux 4.
So what's preferred, sir,
So-
exactly?
That depends on your project goals. If your project goal is speed, you would put it above the multiplexer. If your project goal is area, you would put it below the multiplexer.
Okay, sir. Okay, sir.
Shivendra?
Yes, sir. Also, the leakage power will increase in this case. So why will we prefer this circuit?
As soon as you increase the area, the leakage power would also increase. Yes, you're right. But because the performance would improve, that is why you may want to use this circuit.
The writability.
Writability would improve, write time would improve. For the sense amplifier, if you put it up there, then the what do you say? The time in that you can trigger the sense amplifier will improve. The delay would improve, it would reduce.
Yes.
Anything else?
Sir, in this sense, I can use 4 or 5 sense amplifiers. Sorry, 4 or many number of sense amplifiers as my mux requirement, and I can keep them above for the read operation if I want it to be fast or something.
Yeah. If you want to do it like that, you can do that. But realize sense amplifiers are big circuits. So we'll talk about them today. They're big circuits. If you use 4 of them or 5 of them in every IO, 4 or 8 of them in every IO, it can be a huge area penalty.
Sir, and moreover, we take a long time to write that. Is that the reason why, we are using separate write drivers so that we can increase our speed and read doesn't take that much time?
The right drivers anyway will be separate now, Vaishnav. The functionality and the requirements from a right driver are different from that of a sense amplifier.
Yes. Okay. Yes.
Right driver is expected to be different. Huh?
Yes, sir. Yeah.
Sir, So with the write driver, when I'm writing, I'm taking the, for example, the bit line to 0. I'm discharging the bit line to 0. So if I am basically placing it below the multiplexer, so the additional RC delay that is coming, that will lead to my basically it will take more time to cause that to 0.
Yeah.
So but like before I write, even before I start the word line on, before then only I have pre-charge discharge that bit line, right? So writability, how it is improving. So because even
So
before I start the write, I have ensured that my bit line is
the memory
discharged.
write time will not change. Okay, let us say memory write time will not change. What will change? The time it takes to discharge bit line to 0 has changed. That you agree?
Yes, sir. Yes.
That needs to happen before the word line arrives.
Yes, sir.
So word line, if we say is a clock, then what would this be called? What would this race condition be called typically? If you have a flip-flop,
Yes, sir.
it has a clock as an input,
Yes, sir.
and you say that data should arrive this much before the clock arrives.
So setup condition, setup right.
So if the time to discharge bit line to 0 has increased, what has increased?
The setup time has increased.
Yeah. So data setup has increased. So performance has gotten impacted, no?
Yes, sir.
Performance is not just cycle time. For a memory, you saw the data sheet had so many timings definitions.
Yes, sir.
So
Okay.
that is a performance hit. You're able to see this?
Yes, sir.
Okay. So as I just was mentioning that even when you have just these 6 or 7 blocks there, how you arrange them can have a bearing on the PPA of the memory that you are designing. So now let's start with the circuit designs. Each of these circuits we will look at one by one. Okay. So bit line precharge. One very simple way to precharge the bit lines is put a PMOS which is always on. What's the problem with this?
Static power is there as PMOS are always on.
Yeah, see, look at it like this. Memory is typically off throughout. Hai na? That was the reason why we were also able to remove the PMOSs from that 14T D latch. Most of the cells were always, most of the bit lines, you don't need to, nothing will turn on. Memory is usually off most of the time. Access rate is very low. So one could say, oh, this extra power consumption is only for a very short duration of time. I will still go with it. So power is not really the driving criteria. The fact is that if the PMOS is always on, then the bit line, so now then the discharge, so this is the charging path, and there's a discharge path on the same capacitance, which is the read path. So the memory cell would now have to sync current not only of the original bit line, but also the current that is being injected by these PMOSs, which are always on. So you will not really be able to discharge the bit line to a low level, and you may not be able to read your memory at all in some cases. So the alternate is clocked precharge. When the read operation has to happen or when the write operation has to happen, only then the precharge would turn off. So now there is no race condition, or there is no ratio logic that is happening between the PMOSs of the precharge and the bit cell, which is trying to sync current. Are you able to see how clocking would have?
So this clock is for the read.
Sir, can this clock be word lines?
This is IO region. Will IO region have word lines?
No, sir, but we can consider clock as a word line, right? So
this has to be,
to a
this clock
particular
should
cell.
arrive a little, so this clock should arrive a little earlier than word line actually. So that when the word line comes, the precharge is already off. There is no short circuit path.
Okay, and this is an internal generated signal. Right?
Yes, this is an internal generated clock. Typically, you will call it as precharge clock. So this clock will typically go to precharge circuit.
Okay.
Whenever the active read or write cycle is happening, the precharge would turn off. Okay. So do you notice there is this extra transistor over here? What do you think is the role of this transistor?
So can it be that it keeps both bitline and bitline bar at the same level?
It gives both bitline and bitline bar the same level. What do you mean by same level? It equalizes them.
Yes, sir. Something like that. Right?
So after every clock cycle, it will set them at same voltage level.
Okay. So this additional PMOS is called an equalizer. So that is really the primary function of the equalizer. It ensures that both the bitline and bitline bar are precharged at the same level. So that if you had read a 0 earlier and now you want to read a 1, so the other bitline has to discharge. If they were already equalized, just the discharge has to happen. If they were not equalized, let us say bitline was at 995 millivolts and BL bar was at 10,005 millivolts, 1005 millivolts, then if I now want to discharge this, I have to discharge an additional 10 millivolts in my design. Are you able to see this?
Can you repeat again, sir?
So if I do not have an equalizer, if I do not put this transistor there, can it happen that bitline would go to 995 millivolts and bitline bar to 1005 millivolts? Can it happen?
So I mean,
Because
it will
it
depend
may
on
have
the
happened that I read 1 on this side for the past 100 cycles. And in the past 100 cycles, I read a 0 on this side. So even after whatever time I gave for precharge, my bitline is unable to go beyond 995 millivolts. Can it happen?
So I mean, if my supply voltage is VDD, then both of them will rise to VDD. Na, ultimately, I mean, why is that case happening? 995?
Ultimately could be 5 nanoseconds later also, no?
Yes, sir. So, but like, why it is not? I'm not able to understand that why 995 it is getting limiting by that.
No. So let us say any RC network. You connected a supply over here. Can you tell me when it will go to full VDD output?
Sir, ideally it is infinite.
It will never go to VDD.
Yes, sir.
Hai na? So we know that, okay, 63% it will go in tau. An additional 20% it will go in 2 tau and so on. That much we know. But full VDD, can you tell? Ever?
No, sir. No, sir.
So for bitline, that is what I am saying. 100 cycles have elapsed, and therefore bitline bar was precharged to 1005, already precharged.
Okay, right.
In this one cycle, you read a 0 on this side now. You read a 0 on that side and 1 on this side, let us say. Something like that happened.
Okay, right.
So what is the status? So this one, the bitline would not be able to really, because its precharge is coming and going, coming and going, coming and going. It is not able to really
Right.
precharge to full 100, 1000 millivolts or 1010 millivolts, jo bhi.
Right.
If you have the equalizer, in every cycle, it ensures that the two sides get the same voltage. There could still be an error of 1 or 2 millivolts. That is fine. But an equalizer, the role is to equalize the voltages of the bitline and bitline bar during precharge.
Sir, when is this clock exactly used, sir? Is it used only before read cycle? Because in write, we are supposed to make our bitline to high and bitline bar to low, right? So in that case, this if we give this clock, then both the bit lines will be high.
Both the bit lines will be high. What do you mean?
Yeah, I mean, okay. So in that case, if we give this clock, then both the bit lines will be having the same value. But in right cycle, we should be having one should be at positive VDD and other should be at ground, right? For right
So
cycle.
this clock should go one even during right cycle, na?
Yes, sir. That was my doubt actually.
Yeah,
I mean,
so this clock would go one in all the cycles. All active cycles, this precharge would be turned off.
all
This is precharge clock, na? Let us say this is precharge clock. So this precharge clock has to come in every active cycle. Whether it is a read or a write, it has to come. Yes.
Okay, so after that we'll be lowering or I'm like equating our bitline and bitline bar according to the write or read operation.
So the read, if it is the read operation, the bit lines are already equalized when the
Yes,
precharge clock was 0.
Yeah.
If it is a write operation or if it is a read operation, once you've turned the precharge clock off, now the connection to VDD is gone. Now it's simply now bit line is simply a floating capacitor there.
Yes, sir.
Depending on which side you had a 0 stored, that bit line would discharge, or whichever bit line you want to write a 0, you do it through the write driver.
Okay, got it. Yeah.
Okay.
So, sir, earlier when you were talking that key one bit line is at a lower level, it is a case that that bit line is having basically we are to the right driver in subsequent cycle we are discharging it also and we are charging it also, but other is sort of maintained at VDD. So that is kind of coming, that is able to reach up to VDD, but other is not because it is subsequent discharging to the right time at the right
Yeah,
time.
because for the past 100 cycles, it was continuously in precharge mode. It never got discharged. So it's like kind of, it got 100 cycles for charging of the capacitor. It would charge it closer to VDD, right?
Okay. Yes.
Whereas the other one was charged within just one nanosecond or less than 1 nanosecond.
Right.
Part of it.
Okay.
So it got much lesser time, and therefore this precharge will not be useful VDD. There will be some residual difference between one bit and the other.
The VDS would appear and then it will equalize kind of, sort of.
Yeah. So the equalizer, the VDS would be there, and that would kind of ensure that the charge flows from one bit line to the other.
Yes, sir. So, and one more doubt regarding the Vaishna's question only. So, when for example, my precharge is off, my bit line has been precharged. Now, for example, I'm thinking of the right cycle. So, one of my bit line has to be discharged to 0, and one is that. So, once my precharge cycle is off, now even before my word line comes on, I need to ensure that one of the bit line is off. So during this pre-charge and that word line turning on, during that cycle, difference between the word line, the word driver is like coming to picture and discharging the bit lines.
Yes, the write driver will turn on after the precharge goes off.
Okay, before the bit and before the word line comes on.
Yeah, so you will only after bit line has discharged, you will say my word line will start to rise.
Okay, okay, sir.
Okay.
Sir.
Yes.
So I'm still not able to understand during the write operation how we are keeping a bit line to 0 and the other one to high.
So you do not do it with the precharge transistor cycle. You do it from the you do not do it from this place. You do it from the write driver. We've not even looked at the write driver yet.
Okay. Okay.
This is only the precharge circuit.
Okay, sir.
Okay. So now the next circuit that we look at is column decoder. Okay. So this is a 2-input NOR. This is a column decoder of one type, where you have a 2-input NOR decoder in the, let us say, control region. It generates 4 select outputs. Depending on what A0 and A1 are, either of those 4 outputs would get selected, and you would be able to transfer data to and from the bit lines. What is the challenge here?
Sir, you have shown the bitline pre-charge circuits are here after connecting to the with the decoding.
Bitline pre-charge would be up here.
Okay. Okay. Okay, sir. Yeah.
So there will be bit line, precharge line going over here, something like this. There would be one circuit everywhere. Now what? What is the limitation here? If I say I will use this kind of a column decoder, what is the problem? Very simple
So,
column decoder.
so I
Yeah.
mean, to me, it seems that as we are moving away across the columns, the more RC is coming into picture, and
वो
maybe
तो
that could.
हमेशा ही आएगा. That will always come, na?
Sir, it consists of PMOS only. So area will be large.
Area, oh, PMOS only तो देखा अच्छा बोला, लेकिन area large होगा.
And
होगा.
sir, zero completely नहीं कर पाएंगे हम लोग, right?
Yes, when I want to write a 0, I want to take one of the bit lines to full 0. That you will not be able to do through the PMOSes. So, what is the limitation of this one? So, यहाँ पे आपने देखा कि there is one stage, इसी में आपका MUX4 implement हो गया. हाँ, NOR type of a decoding. There is this another kind of a decoding which is called tree decoding. Huh? And over here, what is happening is that you implemented MUX8. So if this was the case, how many like if I have to implement MUX8 by using this kind of a decoder, how many select lines do I need?
3.
Select lines. Address नहीं बोल रहा. Select lines कितनी चाहिए?
8, sir.
8.
8 select lines. है ना? Actually, you need 16 because S0 and S0 bar. अगर आपका यहाँ पे एक NMOS भी होगा तो S0 and S0 बार भी चाहिए होगा आपको. ठीक है ना? So let us say अभी हम simple ही मानते हैं. We are saying MUX8 होगा तो we would have needed 8 output lines, 8 select lines there. 8 select lines mean in terms of area, at least you need to have the precharge height to be let us say my pitch is 0.1 to 0.8 microns is the height minimum, just because of this metal region. If I go to MUX16, how many lines would be there?
16, sir. 1.6.
So 1.6 micron is the height of the column decoder then. So as I go to a higher MUX, the column decoder area increases very, very significantly. Now let us say I had MUX8. I do not want to use as many lines. I have area constraints, so I now want to use only 6 lines. So I save area, but what is the limitation here?
The voltage levels, sir.
The
We cannot take the output Y to complete 1.
Sir, stack effect because.
यहाँ पे देखो, अगर यहाँ पे आपका sense amplifier लगना है, if your sense amplifier is to be put here, do you realize the bitline or bitline bar voltage has to come from a stack of 3 NMOSes? Huh? Hello? Are you able to see the stack effect there?
Yes, sir.
So this is additional RC. So this device will be slow. And what other thing? What do I mean by this? Any other limitation of this one?
Sir, the Y and Y bar are connected to two different transistors, so there might be some capacitance. I think that's what it's mentioned over there.
See, look at it like this. Now this Y will have to traverse across all the 8 columns. This one signal has to traverse through all the 8 columns. Over here, it has to traverse through 4 columns, and so on. So there are all these additional parasitic capacitances that are coming into picture all over the place. In the previous decoder, there was no such thing. Seedha data bar, one capacitance, that's it. No intermediate wala funda. In a tree decoder, this capacitances are definitely there, but there is also this intermediate capacitances that comes into picture. And that will slow the system down.
Sir, actually, I have some difficulty understanding the. Can you go to the previous slide, sir? So I mean, so these two PMOSes that I'm connecting, why I'm needing these PMOSes for? I mean.
So how will you multiplex the bit lines so that instead of 4 pairs of bit lines, only 1 pair of bit lines goes to the sense amplifier?
So I mean, how? So after the decoder, it should feed into my word line, and that word line should go to the bit cell. So that structure is not getting clear to me from this picture.
So what about column mux? This is column decoder. This is column mux. This is column multiplexer.
Okay, yeah.
We're not in the row decoder region. We are in the IO region only.
Okay. Yes. Okay.
So do you realize there is much extra capacitance in this structure? This is actually going to be much slower. So what is typically done is,
sir, in previous slide, sir. Sir, you said earlier that that PMOS is not going to put a strong 0, right? So why are we not using NMOS here with PMOS also?
Yeah, you have to use. I just said in this implementation it is not there, so you have to use the NMOS also. So you have to use transmission gates.
So sir, I do not understand why we are not using this kind of column decoder.
Who said we are not using? Did I say we do not use?
So sir, I think so. Which one would be better in first column decoder or second column decoder? Because in second column
that
decoder,
depends on your project goals, no, Prince. If
okay,
the project goal is density,
okay, yes,
then that becomes the preferred column decoder. If the project goal is speed, then this could be a decoder of choice.
Okay, got it.
Hana, I am giving you examples. Okay, this is one, this is another, this is another. I am just giving you examples to open you up. There is no one design of decoder. As a designer, you have flexibility. Do you want to exercise that flexibility? Do you want to do design work where there is everything is already frozen for you, or do you want to have the freedom to design the way you want it?
I would like freedom.
Yeah, that is what I am giving you. There is no one answer. Every situation is different. So you would use transmission gates over here. In both the kind of circuits, you would want to use transmission gates so that you can transmit both 0 and 1 well. Okay?
Yes, sir.
So, what we could also do is that implement one stage of mux at the sense amplifier or right driver. So, you remember what we were saying over here? That if the right driver is above the multiplexer or the sense amplifier is, let us say, over here below the multiplexer, then multiplexer could be a 2:4 mux. 2:4 decoder there. Okay, there are 4 lines. You wanted to implement a mux 1, so 1:2 mux could be implemented over the sense amplifier. So what happens? I have to design a mux 8. There are 8 pairs of bit lines coming from the top. The first 4 I will take them to a mux, put a sense amplifier over them. The next 4, I put another mux, and then put a sense amplifier over that. And the second set of this 1:2, this control signals goes here to select which sense amplifier is being addressed. The outputs are buffered after a latch. So what you have essentially done is, you have, instead of a 3-input mux, you've used a 2-input mux, and the remaining multiplexing is being done at the sense amplifier or right driver level. And this then is a area speed trade-off. Are you able to see that? What have I done? I have split mux 8 into two, I have split mux 8 into a hierarchical multiplexing. Mux 4 first, and then sense amplifiers. And the sense amplifier in itself, the enable, is already multiplexed with mixed with address. Okay. Any questions?
So here we are increasing the area to.
Yes, but we are improving the performance.
Yeah, yes. Okay.
By using a smaller mux, I have lesser run of the horizontal signal, so I'm improving the performance.
Yes.
Sir, by using smaller mux, how did you improve performance, sir? Could you please repeat on that?
So if it was a higher mux, in the previous slide, we saw that if it is mux 8, there is a huge capacitance of 8 columns over here.
Okay, got it. Yeah, got it. Yes.
So by using this kind of a composite or hybrid mux, you could achieve better performance. Okay.
Sir, but how I'm paying the area penalty? Is it performance has improved?
You have to add now one additional sense amplifier, na? So that area is extra.
Okay, right.
And if you had implemented a mux 8 directly, one sense amplifier would have worked. But now you have 2 sense amplifiers.
Okay. So sir, like in the earlier classes that you said that, for example, we were doing if we have mux 8, then all the bits of word 0 would be coming to mux 1 mux. Here would be separating that bit 0 into 2 kind of muxes separately. And
Yeah,
then
but
we would
finally one output only.
One output only. Okay. Yeah.
Finally one
Okay.
output only, no?
Yeah, yes, sir. Yeah. Okay, sir.
Okay. So another way could be that अभी तो हमने इस पे implement करा, we could also have it at the latches. Output latch is now multiplexed. Okay. What does that mean? There we will call off something as pages. There are multiple pages. The page which is being accessed, the latch of that particular page would be selected and connected to a global bus.
So what do you mean by page, sir?
Page is an arrangement of, so when we will look at row decoding, abhi is word ko park kar lo. So what did we say? We said that there is a big memory, and in this big memory, there is an array, memory array. Now suppose I need to make a very, very, very big memory. So what would happen? I need to increase the array size very significantly. So word line RC is very high. Even bit line RC is very high. I say that I will split the word line. I will split this particular memory into smaller arrays. This big array I will split into smaller arrays. So what I do is I convert it into pages. So there are 3 pages over here, and these 3 pages go and come here, let us say. Okay.
So how I'm moving the pages? I mean, if we split into 6 pages, right? The whole array.
Yeah.
And
8
then
यहाँ पे 8 कर रहे हैं, नीचे जो एग्जांपल जो कलर्ड एग्जांपल स्लाइड पे दिया है उसमें 8 पेजेस हैं. You just organize them
Yeah.
separately, no? Just like we organized as 2 mux 4s. You
okay.
simply say there are, instead of there being 1000 rows in one array, you said okay, I have distributed 128 rows each. I can do that, na?
Okay.
Sir,
So
what's
it's
the gap in between?
I'm sorry.
Gap. What's the gap in between, sir?
Oh, that is just representational. This is the cartoon. I hope you understand this. This is not the layout. This is a cartoon
Okay.
where I'm saying that as you transition from one page to another, I've just shown that there is space between pages. There will be some strapping that will be done between pages, but yeah, I've just shown it as a cartoon over here to tell you that there are 8 pages.
so somewhat it seems that the intuition seems to be similar to kind of mux. I mean, trying to lower that
Yeah. In
capacitance.
this case, the output latch of each page is where the multiplexing is happening. Which page is output to be selected? So output latch after the sense amplifier is what is being multiplexed. Are you able to see this?
So the addressing here would become a little bit complex because I'm not selecting now the rows on top of that. I'm also selecting the pages. I mean, which page, and then I would select the column, and then I would select that kind of thing.
Yeah.
Okay.
That is when you're writing. If you are reading, then you select the word line, then select which sense amplifier, then you select which output to be taken out on the output bus, and so on. So one is going up, the other is going down.
Okay.
Okay. So this is about the column decoder, and we said that we can, in the IO region, we can organize different parts of the IO differently so that we could arrive at a different PPA. As circuit designers, we have that choice. We also looked at various types of column decoders, and we could choose which we want to use according to the customer requirement, according to the specifications of the memory that you are designing. Okay. Now we come to the sense amplifier. All of us know there is a sense amplifier in the memory, but why is there a sense amplifier?
To
So
sense
too
the
fast.
discharge.
So to improve my read time basically, because
Yeah.
otherwise I have to discharge.
Yeah, if there was no sense amplifier, then I will have to discharge the bit lines to full 0, or at least VDD by 2 to read a 0. Huh? But a sense amplifier, with a sense amplifier, I can precharge the bit line, discharge the bit line only by 100 millivolts, and still be able to read correctly, because that 100 millivolt is amplified by the sense amplifier to a full VDD swing. Are you able to see this? Any questions? Are you able to understand this example that is given here?
Yes, sir.
That when you discharge less, the delay is less. If you discharge more, the delay would be more. And by using a sense amplifier, you're making your circuit faster. When you discharge less, because in the sense amplifier, you need to discharge less only, what else would reduce? So we said performance would, we said the delay would reduce. What else would reduce?
So power consumption, the power.
Power consumption of the bit lines would also reduce.
Yes, sir.
So sense amplifier is a high speed and a low power solution to speed and power trade-off. What goes for a toss is which figure of merit?
So area.
Area. In terms of PPA, performance and power are both improving at the cost of area. Why? Because there are so many transistors in a sense amplifier. So let's have a quick look at how a sense amplifier operates. So this over here is the bit cell on the top. Okay, the word line would come. So this is the word line. It would come when it needs to come. But before that, the bit lines would be precharged to VDD or whatever level you want to precharge them to. Okay? There is the sense amplifier for which SAN is equal to 0. If SAN is equal to 0, there are two PMOSs which are on. And these two PMOSs essentially connect the bit line to the sense amplifier internal nodes. Are you able to see this? When SAN is 0, my bit lines are connected to the sense amplifier internal nodes. Whatever differential appears on the bit lines also appears on the internal nodes of the sense amplifier. When that differential is sufficient, I would take SAN to 1. As soon as SAN goes to 1, these PMOSs also get disconnected. And now this system operates as a latch. It quickly latches the output. A small differential on the bitline bar is therefore amplified into a full VDD swing.
Sir, can you just repeat after just switched from sense amplifier signal from 0 to like 1? What exactly?
You tell me what happens as soon as I switch the SAN to 1. Let's look at this. SAN, so my internal nodes were discharging at a particular rate. I took SAN sense enable to 1. So what would happen now? Till now, this voltage could be VDD minus VT. As soon as this goes to 1, so this latch was not operational. This latch was only operating between VDD and VDD minus VT. As soon as this goes to 1, this becomes a full latch. All the charge over here will get discharged. And this, what do you say? This sense amplifier will be able to read a correct 0 or 1 on the SAF and SAT nodes. So SAF would also come down a little, but it will go back up. Finally, the difference between SAT and SAF would be something like this. Full VDD swing. Is that okay? Any questions?
So how do we know when to make this sense enable 1? Like, is it a particular time or something?
Yeah, so
like
we
after
talked
this.
about, you remember we talked about replica path, reference path?
Yes, sir.
That is how.
Okay, sir.
Okay.
Sir,
So that is
previously,
also being written over here, that you have to carefully tune the reaction time and switch off the sense amplifier to enable start of new cycle. Yeah, there was a question, sorry.
sir, here we have SAF and SAT to 1 previously that we got because we made a read operation previously, and those are the values that we got from the read operation, right?
So this
And
is
like
the
my
read operation
decline-
happening. Sense amplifier operation is a part of read operation. Vaishnav.
Okay.
है ना?
Yes, sir. Yes, yeah. Sir, but okay, so my doubt is that when should the sense amplifier be triggered? It should be, according to me, it should be triggered after the read operation, right?
After
So,
the read operation. What do you mean by after the read operation?
So, I mean, my current should
When does the read operation end?
Sir, after I mean, like BLTI node, after I run my cell current through the BLTI node, so that I have a current so that I can discharge my bit line or bit line bar, whatever, where my zero is
That
stored.
you have done. That you have done. Bitline and bitline bar over here have discharged to. One is at VDD, other is at VDD minus 100 millivolts. Now?
So yes, sir. After that, I mean, like that was my doubt, sir. If I enable my sense amplifier enable, so I do understand there is a PMOS, and I'll be able to run my values into the central node. I mean, like V out and V out bar in this case. So I mean, after that, does that happen in parallel, or I mean, like I see like it's coming from bitline and bitline bar, and it's directly getting dumped into the ground.
So look at it over here. When SAN is equal to 0, is there a ground path?
No, sir.
No, sir.
So it is not directly getting dumped into ground. Now we say SAN goes to 1. SAN goes to 1 means these pass gates have gone off. Bit lines are no longer connected to the sense amplifier now.
Okay.
That is where it is written, important to decouple bit lines from the sense amplifier.
Yes, sir. Got it. Yeah.
You're able to see the functionality of the sense amplifier here? Any questions?
Sir, so for example, during the read, when my this sense enable signal is off, the PMOS are on. So the differential, for example, this BLB underscore mux is sort of discharging, and other one is head LBDT. So sir, the SAF point will, and the SAT point, the SAT point will be basically charged to 1, and the SAT point will be little less, matlab not as VDD. So after we turn off this both the PMOSes, because the SAT is higher point, so it will quickly make that NMOS strong at the SF point, and it will discharge at 0. That is what is happening. And
yeah,
then
actually, you're reading it wrongly. In fact, SAT is discharging more. If you look at it, SAT is discharging more. SAF is discharging like this. SAT is discharging like this. So when this NMOS goes to 1 and the PMOSes get disconnected, what happens? All of a sudden, both sides start to sink current. Because this side had a higher level on the SAF node, the gate of this pull down is at a higher level than the gate of this pull down. Are you able to see this?
so originally my BL underscore mux line was basically discharging. The sort of that at that point it was 0 was stored, so that was discharging. So that's why SAT is discharging more.
Yes.
Okay.
This is just, I'm just taking one example. You could take an example where the other side discharges more. What's the difference there?
Okay.
What's the difference? There's no difference. What is important to realize is whichever side was discharging more, that will continue to discharge faster because of the gate voltage also now.
Yes, as soon as turn my PMOS on, there was more discharge, that will discharge more, and other side would some kind of restore to 1 kind of.
Okay. Yeah.
Yeah. Okay.
So as we said, this one discharges to full 0, the other side goes to 1 because of the latching operation.
Yes, sir. Yes.
Sir, I have a question here.
Yeah.
Sir, does this mean that the internal loads SIF and SAT should be pre-charged as well?
Yes.
Okay. And
you remember
yes.
there is a precharge circuit over here?
Yes. Okay. Okay, sir.
Okay.
And also, should we make, when it comes to sizing of this sense amplifier, should we have the size of this sense enable signal NMOS very high so that it facilitates faster discharge?
Well, okay, so let us say this is 1 micron. So what do you mean by very high for this?
It should be at least greater than 1 micron.
Okay, so you're saying it should be, let us say 1.2 microns?
Yes, sir.
Okay, so अब इससे क्या benefit होगा?
Faster discharge. So, the cell current would be high.
The cell current would be high. So the first of all, when this sense amplifier goes on, we are not connected to the memory cell at all.
Yes, sir.
They have gone off. We are only talking about the sense amplifier.
Yes, sir. I meant cell current means the discharge current, which I meant in the sense amplifier.
So discharge current is being generated in a sense amplifier. What do you mean by that?
I meant the discharge path from SAT to ground. So the current will be
The
large.
latching operation.
Yes.
It's no longer discharge. It is latching operation now.
What does it
So,
exactly mean, sir?
yeah, latching means that one side will go to 0, the other side will go to 1.
Yes.
है ना? So if you keep this transistor to be bigger, you are saying that more current will flow.
Yes.
So okay, keep it a little bigger. No problems. But
Okay.
there's no point to take it so big that it goes to 2 microns. Because at any point of time, only one of the SAF or SAT will go to 0. Both cannot go to 0 simultaneously.
Yes, sir.
Will not. It's
Yes.
a latch finally. So you keep it a little bigger than the pass gates over here or the matched devices over here. That is fine.
Okay. And also, sir, when it comes to the sizing of the transistors in this sense amplifier, so will we follow the same aspect ratio as we maintain in the memory cell, or it will be
Which
even
aspect ratio? Sorry.
the size of pull down the pass gate.
Yeah, why? What is happening here? Are we reading? Are we syncing some? Like, are we reading through the sense amplifier? Is there some data stored inside the sense amplifier that we are trying to read? What is happening?
No, sir, we are not storing any data.
Is there a stability condition around the sense amplifier?
No, sir.
Then,
okay.
See, the structure looks very similar to a 60 SRAM cell, but don't get confused. It's still a sense amplifier. It has a completely different functionality. To design it, you need to consider the functionality that is required of it in your analysis, not the how it is appearing to look or how it is appearing.
Yes.
Okay.
Yes,
So,
Sir.
Yes.
Sir, I just wanted to confirm my understanding, sir. Could you please go back to the previous slide, sir?
Tell me.
So, sir, the precharge circuit which you are using, sir, were you using it to maintain the SAF and SAT at 0?
You tell me.
Sir, it should be 0, sir, according to me.
Why?
Sir, because if bitline and bitline bar, I'm like, they'll be at some voltage and I want them to write on this internal nodes. Then if that's one, then I can't write them directly. In fact, if I on my sense amplifier enable, my the intermediate nodes which I have, that would be reverse driving into my BL and bitline bar, right? Because
Why?
if they are precharged to 1.
In the read operation, bitline, let us say, is at VDD and bitline bar is at VDD minus 100 millivolts.
Yes, sir.
You are saying you want to precharge these to 0.
Yes.
So what is happening? There is this PMOS which is permanently on.
Yes.
SAN has not arrived yet, so this PMOS is on. Can there be a connection between VDD and 0 like this?
No. Sir, okay, understood. Sir, so even if there is a VDD over there, sir, what I understood is that, okay, sense amplifier will be, I think it should be working on a higher voltage than the normal memory voltage which you are working.
No. It is same voltage.
Okay. So, sir, just explain this condition with VDD also, sir, once. Because if I take VDD, then I'm like, I'll be writing back into my VDD minus 100 millivolt, right? And like, even I am not supposed to connect those both nodes directly because they are at different potentials actually. VDD
So
and
what is
VDD.
happening? There is a PMOS here. One side there is VDD, other side there is VDD minus 100 millivolts. The PMOS is on. So what would happen?
Sir, I think
This
that's a
VDD will
dead
also
shot
get
between two
discharged.
different nodes.
This VDD will also get discharged. यही होगा ना? That is what you wanted, nahi? You want to translate the differential on the bit lines onto the internal nodes. Is it that? Is it not?
Yes.
So you want to discharge the internal node, na? What's the problem there? That is your desired functionality.
Okay, so I mean, where is the connection getting completed, sir? Actually, I mean,
The memory
okay,
cell.
and VDD minus 100 millivolts. Okay, that's fine, but there should be a closed circuit when I operate, right? For
The word line is on, no? Word line is on. The memory cell is sinking that current. ये VDD minus 100 कहाँ से आया था? मेमोरी सेल से ही आया था ना?
Okay. Okay, sir.
So basically, I'm translating the discharge on the bit line to this kind of internal node. It is, yes.
Okay, sir.
No.
Got it, sir. Yeah. Thank you.
Sir, can you also please, what was in the slide? There was reaction time mentioned. So what was that?
Reaction time is when I turn the SAN on. After that, after how long will the outputs be SAT and SAS be latched as 0 and 1? That is the reaction time. Okay,
So,
how quickly you can resolve.
So
And
that tune, so that tuning will be depending upon my sizes of these transistors, right?
Yes.
So, okay. So tuning by me, you mean to say that how should I size these transistors? Okay.
Yes.
Okay.
Okay. So now one of the two have discharged. SAT has discharged, SAT bar has discharged. You want to now reset the sense amplifier. The read operation has completed. You want to reset the sense amplifier. For that, you will typically see that there would be this kind of a latch put there. There's an output latch which latches whatever you wanted to write. And then what happens? Now you can वापस precharge your sense amplifier to make it ready for the next read. Is that okay?
So I didn't get it. So I mean,
so there is the sense amplifier. It has these two outputs. So bit lines go in, and these two outputs go out, come out. To start the next cycle, bit lines and also SAT and SAF node have to be precharged to VDD.
yes, sir.
Hai
Yes, sir.
Now there is an output latch down there, output buffer down there.
Yes, sir.
If my SAT and SAF both are precharged to VDD, what will the output buffer do? How will it give an output there? It cannot, na? I cannot connect SAT or SAF because what happens is, suppose SAT went down, SAF remained at VDD. I cannot really connect SAT directly to my output buffer. Why? Because to start the next cycle, I have to take it up. It means my output will only get a glitch, nothing else.
Okay. Yes.
Are you able to see this? There is this analog circuit where the output went to 0. Now, to start the new cycle, you want to take it up. You want to precharge it again. That is when the next cycle can start. But my output bus has to be driven to a desired Q value for much longer time. So what do you need to do? You need to put a latch in between somewhere. And this is the kind of latch that is put. Where even if bit and bit bar both go to 1, the latch will regenerate its contents. It's like an SR latch.
So in the sense amplifier, the SAF and the SAT nodes that were basically I was taking to this, I was taking the output, sir, because it was not evident to me, sir, from that example.
What is the output then?
Okay.
What got amplified from VDD and VDD to 0 and VDD?
So the SAF and the SAT nodes.
So that is the output, no?
Yes. And so these two nodes are you taking to the latch?
Yes.
Okay.
Okay. So that was one set of sense amplifiers. There are other sense amplifiers also, and you can actually spend some time to understand their functionality. Over here, what we have done is we have, instead of the PMOSs, you remember there were PMOSs there? Instead of the PMOSs, we have
Yes,
put
sir.
capacitors. What do you think is the benefit of capacitors? Instead of the PMOSs there?
Sir, I feel there is a, I'm like more than benefit, there is a loss actually, because there is a delay
Yes,
in
sir.
writing the BLB towards the internal node.
There is a
Delay in writing the BLB or bitline or bitline bar towards the internal node actually.
why is there
So,
a delay? Okay.
so
Ma'am,
capacitor.
what is the benefit? Why would one consider putting a capacitor instead of the pass gate?
So like capacitor generally resists change in voltage, right? Resist voltage change. So, but I want to translate that. So wouldn't it be like kind of a counterintuitive, not bad? Because I want to translate that change to the internal nodes.
Is this a coupling capacitor or is this some loading capacitor?
Coupling, I think, sir.
Coupling capacitor.
So what does a coupling capacitor do?
Couple the voltage from one side to the other.
It will couple the voltage on the bit lines into the internal nodes.
Okay, yes, sir.
Sir, I think DC stabilization might be the case, because we are isolating the DC voltage between the top and the bottom thing, so might be the case.
So see, the memory array, you may want to operate at 1 volts, because below 1 volts, the memory cell will not function. But sense amplifier, you can operate at 0.6 volts also, because it's a circuit which can function at 0.6 volts also. The latch can function. In the previous design that we looked at, bitline and SAT and SAF nodes were connected with each other during the reset mode. What that also meant was that they had to be at the same voltage. You could not operate the sense amplifier at a voltage different than the memory array. Are you able to see this?
Yes, sir.
By decoupling them, now you say, oh, even if your memory array needs to go to 1.0 volts, my sense amplifier can operate at 0.6 volts also. So let us do DVFS. Only this VDD will go low, that other VDD will not go low. So you save power. Another way to achieve a similar independence of voltage of sense amplifier and bit lines is this one, where the bit lines go to the gate of a device. They are never connected to the output nodes over here. Okay. And you will see both the sense amplifiers are used. Any questions till here?
So how I'm decoupling them? So I mean, so initially the SAN, sir, we were towards the discharge kind of the decoupling, and this one, sir. Yes.
Yeah. So in the reset mode, what is the status of BLB and SAF?
So both are like pre-charged. Yes.
Pre-charged and connected. Because sense enable is 0, so they are connected in a way.
Oh, yes, sir. Yes. Yes, sir.
Now, by putting a capacitor instead, can they ever be connected electrically?
No, sir.
They can be at different voltages then.
Yes, sir.
Hmm?
Thank you, sir.
Anything else? Ranjit, your hand is raised.
Sir, why is this output lines pre-charged in the second case?
In the second case?
Yes, we have P4 and P3 MOSFETs.
Because you want this latch to be operational, no? So it's just like you're saying that this latch will start from VDD at all times. The latch will need to be pre-charged. But that VDD, this VDD P can be different from the VDD array over here. So this could be VDD P again. The voltage of the sense amplifier can be different from the voltage of the array, of the bit lines.
Okay.
Okay. So again, for this also, you can see a paper in my Google Scholar page. You will see there's a paper on gauge coupled sense amplifier. There's a patent also around it. So you can study that and get a better view. Okay. Another thing that you should notice is that there is, because now I am not worried about what the voltage of this Vout and Vout bar is. I can actually equalize it to a Q point, to its Q point. So you see there are no two PMOSes over here. I just have an equalizer. A Q point equalized SRAM was found to be faster than the precharged SRAM, precharged sense amplifiers there. Okay. So the last slide on sense amplifiers. In a SRAM, we have discussed that there could be, say, one sense amplifier per MUX4 or MUX8. In a DRAM, it is not possible. In a DRAM, you have to put a sense amplifier for every column. So if you have to put a MUX, it has to be below the sense amplifier. Okay. Why can't we use a multiplexer before the sense amplifier in a DRAM?
So in that case, we'll have for 4 columns, we'll have a single SRAM. In that case, if we use that way.
In that case, you would have?
We'll have a single sense amplifier for 4 columns, which violates this statement.
So, sir, you're talking about the DRAM, sir.
DRAM.
So, sir, like DRAM only, we have like capacitor. So, I mean, because earlier when I was putting like sense amplifier after the multiplexer, there was a performance degradation. So, sir, but because now we have the charge thing, so I think that because they're discharging, it becomes more kind of logical to place above that, because that loss of charge and I'm getting more RC, maybe
So think about it. Think about it. Let me give you a hint. In DRAM, when you read, it is always a destructive read. So we will discuss DRAMs in a little, after a few lectures. Don't worry. I will anyway give you the answer to it. I'm just picking your curiosity as of now. Okay. That in a DRAM, you have to put a sense amplifier on every column. For an SRAM, you can save area by putting it after the multiplexer. Okay.
Yes. Okay,
sir.
Yes.
Sir, we generally say DRAM is much dense, right? Sir, itne sare sense amplifiers we are using, so how does that become dense actually?
Is it the density of a memory because of the periphery or because of the memory cell?
Sir, matlab, if we buy a DRAM, we'll get it with the sense amplifier, right? Memory अकेला थोड़ी देगा वो मतलब.
हाँ, तो पूरी मेमोरी के अंदर how much area is of the periphery and how much area is of the memory array.
हाँ वो तो ठीक है सर, मतलब ओके मेमोरी का तो कम है सर इसमें, वो है, बट इन टोटल पीसी द साइज is being large, right? Sense amplifier size. Sorry.
Of the periphery, yes. So let us look at it like this. Let us say for an SRAM, the area of the array is 9, area of the periphery is 1. Total area is 10.
Okay.
For a DRAM, that 9 would shrink to, let us say, 2. Okay. Periphery you made from 1 to 3 also. Let us say, आपने periphery 3 times भी बड़ी कर दी. What happened? Total area is now 5.
Okay, sir. Comparatively,
half the area, na?
Yes.
So I'm just giving you some random gross cartoon types numbers. That is not the reality. Even in a DRAM, the array is much more area than the periphery. But just I'm exaggerating the situation for you. Okay. There are two different components for area. Periphery area is larger. Okay, understood. But what about the array area? Array is so dense that overall DRAM is denser. Okay. So we'll close here and we will do write driver and closure of the IO circuits in the next class. Okay.
So like, do you have time, sir? Because I need to ask regarding the column decoder one they were set out. So.
Okay, you want to ask now or you want to ask in the office hours? You want to ask now? Just give me a minute.
So just want to see because it was so that I can think about that.
Let me close the class. Let me close the class.
Sure, sir.
Yeah. Just give me a minute.